We're going to start on Chapter 2 today, and the title is Atoms, Molecules, and Ions. The topics for Chapter 2 are listed right here. We have early atomic theories, simple atomic structure, isotopes, periodic table, Bohr model of the atom, the octet theory, ions, molecules, and formulas for compounds. Let's start then with the early atomic theories. No one really knows where the idea of atoms has come from, but Democritus gets the credit for it, and he was around 400 BC in Greece. Democritus thought that if you took matter, you could break it down into smaller and smaller particles, but eventually you'd wind up with some basic particle, which he called an atom. It's actually from the Greek word atomos, which means indivisible. Democritus thought that atoms differed in geometric shape, as you can see up here on the screen, and that atoms could stick together because of these little hooks that they have. You probably got this from studying nature. We know that if you walk through the woods, you might get some burrs stuck on you. And burrs, again, give rise to Velcro in our day. Jumping up now to almost 1800, we see Antoine Lavoisier. He did some experiments where he found that matter didn't seem to change after a chemical reaction had taken place. He didn't know why that was happening. That got him to formulate the law of conservation of matter. At that time, most people thought that this wouldn't be true. In fact, the evidence around them said it wouldn't be. Here's an example. If you take some wood and you weigh it, and then you burn the wood, the ashes that you get produced at the end from burning don't weigh anything near the wood did before you burnt it. So people thought that masses did change when chemical reactions happened. Also at this time, Joseph Proust in France worked with some compounds. He found that whenever he decomposed compounds, he always got the same ratio by mass of elements in these compounds. It never varied. He didn't know why either, and that took John Dalton, 1800, to come up with an idea why. So Dalton thought that if matter were made up of atoms, that may explain it. Dalton thought that atoms are small, round, and hard like billiard balls. Each element has its own atom, which really differ in weight, and atoms stick together to form compounds. Now here's an example. So let's say we have two elements, X and Y, and according to Dalton's idea, element X is made up of smaller atoms in element Y, so element X, those atoms weigh less, and that's why on the diagram here we see smaller red balls versus the larger green ones. And then element X and Y can combine together to form a compound. And in the compound, the ratio is 2 atoms of X to 1 atom of Y, kind of like water. Now you notice that he's starting with 16 atoms of X and 8 atoms of Y. And when they combine together, wind up with 8 molecules of this compound, but where the total atoms are 24, which matches the total atoms that we started with. So Dalton's idea would explain what Lavoisier had seen. The mass before the reaction and the mass after were the same. It would also explain what Proust had observed, in that the compounds wound up with the same mass ratios. J.J. Thomson in 1897 discovered the electron. This was the first particle of the atom that was discovered. So he tried to reason, where could these electrons be coming from? And at the time, people believed that matter was made up of atoms, but they were using Dalton's idea that atoms are round and hard and very dense. But if electrons are able to escape from these atoms, maybe the atoms aren't so dense anymore. So Dalton thought that if they could escape from the atoms, maybe the atoms are more fluid. So here is Dalton's model of the atom. It's called the raisin pudding model. Dalton thought that an atom was more like a pudding, and that pudding contained a positive charge that would offset the negative charge of the electrons. The electrons are viewed as raisins embedded within the pudding, but because the atom is soft, the electrons can easily escape from it. That was a nice attempt at explaining what people had seen, but it's not going to last too long. Now around this time, Ernest Rutherford, in 1910, discovered the 3 basic types of radiation: alpha particles, beta particles, and gamma rays. Now here is the difference between these three. If you take a radioactive material and encase it in a lead block, let's say there's only a pinhole on one side of the block so that the radiation can escape through that. If you take and put a negative plate at the top and a positive plate on the bottom, as the radiation goes through there, we can separate the different types of radiation from each other. So at the top we have an alpha particle, that's the Greek letter A for alpha, and because it's being bent up towards a negative plate, an alpha particle must have a positive charge. And at the bottom we have a beta particle, and it's being bent towards the positive plate, so a beta particle must have a negative charge. And you notice the middle one, the gamma ray, isn't affected at all by these plates, so a gamma ray must be neutral, and indeed it is. Now Rutherford wanted to do some experiments with radiation, and one of the things he wanted to do was to verify the idea of atoms that Thomson had. And actually Rutherford worked for Thomson. And so he thought he could shoot his radiation right through a sample of matter, and because matter is made up of these fluid atoms, he expected all of his radiation to pass directly right through it. And this was his setup. Now he has his lead box and he has his radioactive source in there, and the radioactive source is emitting alpha particles. And he has a piece of gold foil, very thin piece of gold foil, surrounded by this screen that has a coating on it that will glow when it gets hit by alpha particles. So remember that Rutherford thought all the alpha particles should pass right through the gold foil. But let's look at the results. You notice that some of the particles were scattered to the sides, and actually a couple came directly back. And this was amazing to Rutherford. He explained it as if you had shot a gun at a piece of tissue paper and a bullet bounced back and hit you. That's how surprised he was at these results. So how could he explain it? Rutherford said that Thomson's model of the atom must be incorrect. So he said, an atom must be mostly empty space since most of my particles went right through it. But the atom must have a dense positive part of it, which he called the nucleus. And that would explain why some of those particles were deflected to the sides. Because alpha particles are positive, they'd be deflected by a positive nucleus. And every once in a while a particle might come directly back at you, and he said that particle almost hit the nucleus. So these were his conclusions. And now, as you see, we're getting closer and closer to the model that we have today. So here we have our basic atom with a nucleus in the center, which contains protons and neutrons, surrounded by an electron cloud. The electron cloud gives an atom its volume, whereas the nucleus gives an atom its mass. It isn't worthwhile measuring the mass of protons and neutrons in grams, so a unit called an atomic mass unit, or AMU, was created. This is just a relative unit. Now if you look down at the masses on the screen, if a proton weighs one of these AMUs, a neutron weighs almost one AMU. In fact, it's a little bit more than one, like 1.04. An electron weighs almost zero, almost nothing, compared to a proton and a neutron. Now, it has to weigh something, but because the mass is so little, it doesn't really add to the mass of the atom. And then we have the charges we see. The proton is assigned a charge of +1, and an electron charge is assigned of -1, and a neutron will be neutral. Now, here are two terms that you really want to make sure you know. Atomic mass is the number of protons plus the number of neutrons. And atomic number is number of protons, and it's also the number of electrons. This will be true in all atoms. Now, here's an example. AU is a symbol for gold, and we all like gold. Now, we have two different numbers that are given with the symbol. The top number is the atomic mass, and the bottom number is the atomic number. The atomic number of gold then is 79, atomic mass 197. Number of protons and electrons then would be 79, since they match up with the atomic number. Now how do we get the number of neutrons? Well, for that we're going to subtract the atomic mass minus the atomic number. So for this particular gold atom, it would have 118 neutrons. So out of these three particles, protons and neutrons and electrons, which one determines the identity of an element? Well, as it turns out, it's the protons. Every element has a unique number of protons. If that number of protons changes, the element changes. Electrons and neutrons, as we're going to see, they can vary. Are all atoms of an element the same? Let's check out some atoms of carbon. We can have 3 different isotopes of carbon. You can have carbon-12, 13, and 14. Carbon-12 would have 6 protons and 6 neutrons in its nucleus. That's what the 12 means. And would also have 6 electrons outside it, offsetting the charge of the 6 protons. What about carbon-13? Notice carbon-13 has 7 neutrons versus 6. So the 7 neutrons and the 6 protons gives us the mass of 13. And for carbon-14, that would have 8 neutrons. So these are 3 isotopes of carbon, and chemically they're all exactly the same. They just differ in the number of neutrons. Now, because the number of neutrons is different, some of these isotopes will be radioactive. And as it turns out, it's carbon-13 and 14. Both of those nuclei are unstable, and they release radiation as they're trying to get the number of neutrons or protons in a better ratio. Carbon-12 makes up almost all the carbon that we see on this planet. And one way you can tell that is if you look at the front of your book and look up the atomic mass of carbon, you'll see it says 12.01. Now those atomic masses are averages based on the number of different isotopes for an element and the percent that those isotopes exist in nature. So because the atomic mass listed is 12.01, it's telling you almost all the carbon on this planet is carbon-12. Now here's another way to represent carbon atoms. It means the same thing as we saw before: atomic mass with the numbers at the top, and atomic numbers are the numbers on the bottom. So, isotopes then, atoms of the same element that have a different mass. And the mass is due to a different number of neutrons. Now let's take a moment out for you guys to try these. So you want to write down the number of protons and neutrons and electrons in each of the following. You can use your textbook if you need, so for a periodic table or a list of atomic numbers. Now once you come up with your answers, then we'll go to the next slide. So you might want to pause right here. Okay, now next slide with the answers, and here we see. So how did you do? Make sure you check these out, because this is one of the things you're going to be able to, one of these things you're going to be asked to do on the next exam.